Okay, so a couple things. I got your quizzes graded. Quizzes were recorded in Moodle. If you're in the room here right now, I have it to give back to you. If you're not here in the room right now, I have it to give back to you. You can just come and get it in person at some point. Cool. So that's my first announcement. My second announcement. So oh, you want to see? Okay. Thanks. So quiz scores are recorded. The other announcement that I have is next Monday, classes on Zoom for everyone. I don't love to hold classes on Zoom, but I've got to go to Atlanta for a couple-day conference next week. And so I will just be ducking out of the conference, going up to my hotel room and Zooming with y'all. And it'll be fun for me. This will be in my email reminder on Thursday, though. By no means do I expect that you're going to track that. Questions so far? I love it. Look what I just got. Look what I just got. Whoa. I got a raspberry muffin. Thank you. Cool, huh? Does anyone want part of it? I'm happy to share. Okay. So, you ready? All right, I'm excited. We get to do chapter 4. This is like such a fun chapter. Chapter 4 is on exponential and logarithmic functions. Now, people ask, why don't you go through this class in order? Right? Why aren't you doing chapter 3 after you do chapter 2? Oh, hi, Van. Van, real quick, just thanks for zooming in. And the quiz scores are recorded. You can get them back when you come to class. And next Monday, class is on Zoom for everyone. Okay. So, the reason why I do chapter 4 after I do chapter 2 is I really, really enjoy contrasting exponential functions with linear functions. Okay, so, and I'm going to do that very explicitly with all of you right now. But I think it's most interesting, and it's also most insightful when you talk about exponential functions as contrasted to linear functions. Okay, various things grow linearly, but a lot of things in the real world, like population, grows exponentially. If you're growing bacteria in a petri dish, that grows exponentially. If you're talking about like radioactive decay, that decays exponentially. So what I want to do is kind of get into what the differences are between linear growth and decay versus exponential growth and decay. Now, the one common characteristic of linear growth, which was on your quiz last week, is that it has a constant rate of change, right? Grows by the exact same amount or decays by the exact same amount. Exponential growth has a constant percentage change. So we say that it grows or decays by a relative amount. Okay. And I think that the best example that I can give is, you know, suppose there's a group of people and everybody gets a $5,000 salary increase per year. That's pretty sweet, huh? Doesn't everyone get an increase by the exact same amount? Okay, so let's compare two people. So person one is an administrator and they make $150,000 per year. And person two is an advisor and they make $35,000 per year. Okay. If both people get a $5,000 raise, then this person ends up making 155,000 and this person ends up making 40,000. Okay, still pretty decent, but this 5,000 is a lot more significant of a raise for the person who makes $35,000 a year as opposed to the person who makes $150,000 a year. But this is if it grows linearly. If it grows exponentially, suppose everybody, okay, well, let's just talk about the Montana University system. The state legislature gives us a raise every year. We get a 2% raise per year. And while that's nice, it certainly doesn't meet inflation by any stretch. But what does a 2% raise mean? Well, it means that this person who makes $150,000 adds on 2% of $150,000. Okay, and 2% of $150,000 means they're getting a $3,000 raise. Okay, not as good as getting the $5,000 raise. But how about person two? Well, they make $35,000. They also get a 2% raise, but it's not as significant because a 2% of $35,000 is only $700 raise. So in the end, this person makes $35,700, whereas this person makes $153,000. So when you're taking a percentage, it's relative. Okay, it sounds like it's fair and equitable that everybody gets a 2% raise, but 2% of not very much is not very much. You with me here? Okay. Eric, just to keep you up on the announcements, quiz scores were recorded. I'll hand them back. And next Monday class is Zoom for everyone. So we're going to get into the difference here between the two. And I'm going to start with a really tame example. I'm going to say that suppose we have town one. And town one starts with 100 people. And suppose this town adds 25 people per year. Nobody dies. It's just 25 people. Okay, let's talk about this town. In year zero, when this town was first started, how many people were in the town? 100. Okay, in year one, what happened? Well, we had those 100 people, but what happened? We're adding 25 people on. Wow, we have a total of 125 people in town. In year two, now what's our starting population? 125, and now aren't we adding on 25 more? In other words, we have 150 people. We could look at it as though we have 100 people, our rate of change is 25 people per year for 2 years. In year 3, well, how many people are we going to have? 175. In other words, we start out with 100 people. We grow by 25 people per year for 3 years. Okay, this should be familiar. And we can say in general, we can write a linear equation for this. If X represents the number of years since the town started, what's my slope? 25X plus 100. It's always nice when you talk about something new to start with something familiar. Okay, so what's nice about writing an actual function for this? Well, we could say, well, Lauren, what happens in year 10? Instead of going through year 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and keeping on adding 25, can't we just plug 10 in for X? And say, wow, there's 350 people in that town after 10 years. You with me there? Okay, so that is how things look with a linear. It has that constant rate of change. Okay. Questions here? Okay, so now let's talk about town 2. Town 2 also starts with 100 people. But now what it does, it adds on 25% per year. So I kept the numbers the same, 20 and 25. But now what we're going to do is look at the differences. Okay. And what I'm going to do here is I'm going to write out a fair amount of things, and it's going to be like, why are you making things look more complicated? But what I'm really trying to do is establish what these functions do and what their characteristics are. And if you're wondering, what do I mean? Well, notice this B value here is our initial population, and this number right here is our growth rate, correct? Okay. So keeping track of that. So let's talk about year 0. This is the easy part. How many people were there? 100. In year 1, well, we started with 100 people, but we're growing. So I'm adding on what? 25%, right? 25% of what? Of 100. Remember, of in math means multiply. So we have 100 people, and then we're adding on 25% of those, and it equals 125. I'm less concerned about that right now, but I want to show you something here. Y'all with me this far? Okay. Do you agree I have 2 terms here? Terms are things separated by plus or minus signs. Do you agree I have 100 in each of these terms? So I'm going to pull it out. Remember the anti-distributive property, factor out a common factor? If I pull 100 out, in other words, divide each of my terms by 100, what do I have left in my first term? 1. And if I divide my second term by 100, what am I left with? Aren't I left with just the 0.25? So we can write this as 100 times 1.25, which you're like, okay, Lauren, that's 125. Why are you making things look complicated? Just hold on to that. Are there any questions this far? Okay. What I want you to do is note that this is the more complicated way of writing 125. So now let's talk about year 2. How many people did we start out with at the top of year 2? 125 people, and holy smokes, we're adding on 25% again. So now we take 0.25, 25% of what? Of 125. Do you see how we're taking a percentage of a bigger number? Now, I don't really care that that's equal to 156.25, but I'll tell you that anyway. What I want to do is I want to do a similar thing. Don't these two terms have 125 in common? So I'm going to pull it out. And if you're asking why, I'm just going to tell you because I'm developing a formula. If I pull 125 out of my first term, what am I left with? 1. If I pull 125 out of my second term, what am I left with? 0.25. So do you agree this is the same as 125 times 1.25? Now, this is where it's going to look like I'm just going in weird directions here. Remember how I underlined this up here and said that's 125? What I'm going to do is I'm going to plug that in for 125 right here. In other words, I'm going to make this look even more complicated. So in place of 125, I saw that was 100 times 1.25. That's this 125. And now I have this other 1.25. Can't I write this as 100 times 1.25 squared? Why? Because what does it mean to square something? Don't you take it and multiply by itself twice? You with me there? All right. And so we can then do year 3. We know that this is equal to 156.25. So in year 3, we're starting out with 156.25 people. And what are we adding on? 25% of that 156.25. Note, I'm going to follow the same pattern. I'm going to yank out my 156.25. What am I left with in my first term? 1. What am I left with in my second term? 0.25. So don't I have 156.25 times another 1.25? Doink, 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 doink. See, doing tonight. All right. Well, wasn't this another way of writing 156.25? So I'm going to plug it in there. Again, you might ask why, but I'm hoping you're going to see the pattern. So in year 3, in place of 156.25, I'm going to write that. And then I have another 1.25. When you multiply two things with the same base, what do you do to your exponents? And not that we really care, but you get 195.3125. So I want you to notice a pattern here. In year 0, we had 100 people. In year 1, we had that initial amount times 1.25. Raised to what power? The first power. In year 2, we have this initial amount of 100, but now I'm taking this 1.25 and raising it to the second power. In year 3, I have this 100, and now I'm taking this 1.25 to the third power. Okay, so what I want to summarize is this. Here's 100, and we could say that's 1.25 to the 0 power. What's anything raised to the 0 power? 1. In year 1, we had 100 times 1.25. In year 2, we have 100 times 1.25 squared. Year 3, 100 times 1.25 cubed. What is this value of 100? Wasn't that our initial value? Okay, this exponent, do you see the relationship between the exponent and the year? And where did this 1.25 come from? Well, I claim that it means that we took 100% of our starting population, and then we added on 25% of our population. 100% in decimal form, do you agree, is 1? Our growth rate in decimal form is 0.25. So it's 1 plus the percent growth. So what would be my population in year 10? How would I compute that? To the 10th power. And if you do the computation, you'll see you're going to get about 931 people. So just as with our linear functions, there's a pattern here. Okay. Now, something I want you to note is initially in year 0, whether I have my linear or my exponential, I start with the same amount. In year 1, it's the same amount. In year 2, it doesn't even differ by very much. In year 2, we had 150 people. And in year 2, we had 156.25 people. Okay. In year 3, they're going to differ by a little bit more of an amount. In year 3 with the linear, we had 175. And here we were at 195.3125. But look at what happened after 10 years. In the linear town, we only have 350 people. And look at what's happened in our town that's grown exponentially. It's getting big. Okay. So the moral of the story is as follows. With linear growth or decay, again, it grows or decays by a constant rate amount. And we have y equals mx plus b. M is our rate of change. And b is our initial value. On the other hand, with exponential functions, it looks a little different. Okay, this grows or decays by a constant percentage, but that makes it a relative amount. And the way our exponential functions look is we write them as a times b to the x power. This A, this number in front, is our initial value. Okay, notice when we were doing this computation here, this 100 was our initial value. That's our starting amount. Okay, now this B, and do you agree that if you plugged in X equals 0, so if I compute F of 0, it's A times B to the 0 power. What is B to the 0 power? 1. So again, you get your initial value. B is called our base or our growth and decay factor. Do you see here when we were growing, we had all of the original and then we added on the percent growth? Okay, so when you're growing, B is greater than 1 when you have exponential growth. And B will be equal to 1 plus R, where R is the percent growth rate. It turns out when you have exponential decay, your B is going to be between 0 and 1, and it's equal to 1 minus R. So in sum, and we'll do a bunch of decaying. We do that as humans. Okay, this is what an exponential function looks like. Again, the number out in front is our initial value. And B is equal to 1 plus or minus R. Again, B is equal to 1 plus R when it's growth. And B is equal to 1 minus R when it's decay. And let me motivate this for you right now. Okay. Because I showed you how that 1 plus R just naturally comes on. I got to show you where that 1 minus R comes from. So suppose we start with 100 milligrams of some substance. And suppose it decays by 10% per year. Already, I know this is exponential because I see that percentage. You with me there? Okay. Well, in year 0, how much substance do we have? 100. In year 1, what happens? Well, I started out with 100 milligrams, but now it decays. So I'm going to subtract. What does it decay by? 10%, right? So isn't that 10% of that 100? In case you care, that means we have 90 milligrams left. But watch this pattern again. See how I have 100 in each of my terms? I'm going to pull it out. Same as what we did with the population growing. If I factor 100 out of my first term, what am I left with? 1. If I factor 100 out of my second term, what am I left with? 0.1. What is 1 minus 0.1? 0.9. Okay. And following what we had up here for exponential decay, we have 100%. We're subtracting off 10%. Doesn't that give us 90%? Are you all with me on this formula? Like, I don't want to like beat it into the ground, but in the same sense. Do you see how it comes naturally?
Yes.
Cool. Cool, cool. All right. Now, I want to make one quick contrast before we move any further. There's a difference between these two functions. It looks like a very fine difference, but it's actually huge. Okay. Notice they both have bases and they both have exponents. This is a power function. This is one of our toolkit functions. It's a polynomial. We've played with the graph of it starting in chapter 1. That's our general parabola. Okay, why is that a power function? Notice my exponent is constant. What varies is my base. This is an exponential function. You know you have an exponential function when your exponent is the variable. And you're going to see, because we're going to be playing with these graphs a lot, that this is essentially what exponential functions look like when you graph them. You with me this far? All right, now what I want to say is if you are not hip on your properties of exponents, you want to be. Okay, so right, when you multiply two things with the same base, you add your exponents. When you raise something to a power, raise to another power, you multiply your exponents. Don't forget your properties of exponents as we proceed through this. Okay. All right. So let's just practice with familiarity with this formula for a little bit. Suppose I tell you that I have this exponential function. And what I want to know are two things. What is my initial value? Good. It's this number out in front. Is this growing or is this decaying? It's growing. How do we know it's growing? Because our base is greater than 1. Okay. Now, if you want to know what your growth rate is, you're going to get to a point where you can just look at this and you're going to say, well, B is 1 plus R, isn't it? And that's equal to 1.09. You can literally solve for R here, can't you? Subtract 1 from both sides. So you're going to get 0.09. In other words, in this example, we have an initial value of 5 and we have a 9% growth rate. What if I have this? Okay. What is my initial amount in this next example? $300. Y'all with me here? Okay. Is this growing or is this decaying? Good, it's decaying. How do we know? Because our B is between 0 and 1. Now, when it's decaying, remember, B is equal to 1 minus R. So if I asked you what is the decay rate, it's not 77% decay rate. That's your B value, which is 1 minus R. Can we solve for R? What would we do? We would first subtract 1, and 0.77 minus 1 is negative 0.23, and that's equal to negative R. But we don't want negative R, we want to know R. So what do? Multiply or divide by negative 1, and don't we get R to be 0.23? In other words, this had a decay rate of 23%. So my moral at this point is when you're growing, you can pretty quickly read off what the growth rate is. When you're decaying, you got to subtract it from 1, and that's your decay rate. Y'all with me this far? Okay, it's really important to get comfortable with these functions. So check this out. I wrote this exponential function down a little bit ago. Let's talk about it. And you're like, what do you want to talk about, Lauren? Well, I want to talk about what my initial value is, whether it's growing or decaying, and then what that rate is. Now, if you're a little perplexed right now, you're like, wait a minute, there's no number out in front. Can't I rewrite this as 1 times 2 to the x power? If you wouldn't have thought of that, well, hopefully there's a point to coming to class. So what's my initial value? 1. Is this growing or is this decaying? Well, how can you tell? Look at your base. Is your base greater than 1 or is it between 0 and 1? It's totally growing because B is greater than 1. In fact, B is equal to 2. So I'm going to say 2 is equal to 1 plus R. Can I solve for R? Yep. What do? Subtract 1 from both sides. So 2 minus 1 is 1. What's my growth rate? Change this to percent form. It's growing by at 100% growth rate. B cannot be negative. By definition, B has always got to be greater than 0. Are you with me this far? No? Oh, okay. Okay. So right now, what I'm just trying to get us to do is gain some familiarity and some comfort with this function. So what I've been doing for the past couple of examples is writing down the function and having you identify the initial value, whether it's growing or decaying, and what that corresponding rate is. Now, what I'm going to do is change it up. I'm going to tell you, suppose our initial amount is 11,000 and it grows by 8.5%. And now what I want us to do is write the equation of that function. Again, I'm doing this just so that you start getting comfortable with what the A and the B represent. Well, what is my A? A is 11,000. Okay. Now I need to find my B. Remember, since I'm growing, B is equal to 1 plus R. What is my R value in decimal form? We get 0.085. So don't I get B to be 1.085? You with me this far? Okay. So suppose I give you that the population of something in 2010 was 23,900. And suppose it's growing by 9% per year. Okay, so what if I ask us, for example, to estimate the population in the year, how about 2022? The first thing we want to do is write out what the equation of this function is. Because my population in 2010 was given to me, I'm going to let that be my initial population. Okay. Now, if I let that be my initial population, that necessitates me defining my variable to be the number of years after 2010. Okay, what's my base here since I'm growing by 9%? $1.09, and then we have to the X power. Are there questions how we got 1.09? Okay, so if I want to find the estimated population in 2022, what do I plug in? X equals what? Well, why? Because again, I'm using this as my initial population. So I'm defining X to be the number of years later. So what we would do is we would compute this. And not that we really care what the answer is, but we'll compute it anyway. We are going to get about 67,000. I'm rounding to the nearest whole number. 223. Can we do one more? Are you all okay this far? Yeah. Okay. I mean, if you want to wait to do one more on Wednesday, all you have to do is say it. All right. Well, let's pretend we purchase a car for $32,500. Wow, I've never spent that much. And the thing about cars is they actually depreciate in value. So suppose it depreciates by 5% per year. And I want us to find the value of the car after 12 years. Well, before I even do this, I want to find the equation of this function. Do you agree it's exponential? How do we know? The percentage. Good. Okay, notice it's going down in value. So I'm going to say that my initial value, in other words, in year 0, isn't it 32,500? But because it's depreciating, isn't my B equal to 1 minus R? What is my R value here? 0.05, and 1 minus 0.05 is 0.95. Notice it makes sense that it's depreciating because I got a base between 0 and 1. So to find out the value after 12 years, what would we do? Wouldn't we plug in x equals 12? So we would compute 32,500 times 0.95 to the 12th power. And in case you care, you're going to get approximately $17,561.70. My car after 12 years would not be worth that much, but I tend to hit a lot of deer accidentally. All right. So what I want you to note is one thing at this point. It's pretty sweet when we're given the initial value as well as the growth or decay rate, isn't it? Yeah. So enjoy that sweetness until Wednesday. Okay. I hope you have an awesome day, and